Please take a seat, everybody. Thank you for coming. My name is Paolo Bocchini. I am an associate professor in the Department of Civil and Environmental Engineering here at Lehigh University. And we're here for the Objective Resilience Lecture of the American Society of Civil Engineering and of the Engineering Mechanics Institute. So we're going to talk about resilience. And resilience, I believe, is really about raising the bar. In the past century, the goal of structural engineers and civil engineers in general was to preserve lives. And they have been very successful in improving a lot the standards and protecting lives, even in the case of extreme events. But then the society, as this goal was almost achieved, started asking for more and expecting that our structures and infrastructure systems were not only preserving life, but also delivering continuous functionality, or at least they were able to be restored to full functionality very quickly. And this required a complete change of perspective for civil engineers. So first of all, functionality makes a lot more sense at the system level. And so it was a change of scale of the type of things that we were doing, from the individual structure to the systems of structures. And second, it required to work in a lot, in a way that is a lot more interdisciplinary, because functionality involves also the society, involves economic considerations, etc., and required a big change also from this point of view. And I'm very happy that Dr. Padgett came here to give this lecture, because I think that she's one of the engineers that embraced this change of perspective best than most others. I'm also very proud that ASE and EMI and the Objective Resilience Committee decided to ask Lehigh University to host this event. I see this as a recognition of the fact that Lehigh, our Department of Civil Engineering, was one of the first that moved full speed in this direction and continues to try to promote this change of perspective for our profession. Today, to represent the American Society of Civil Engineering and the Engineering Mechanics Institute, we have the director of EMI, Dr. Amar Chaker, that will come and say a few words.
Thank you, Professor Bocchini. Welcome. Thank you for coming to this lecture. My name is Amar Chaker. I am the director of the Engineering Mechanics Institute. That's one of the 9 specialty institutes of ASC that focuses on applied mechanics, solids, structures, fluids, which is really the basis for much of what civil engineers do, whether it's structures or geotechnical engineering or water resources engineering. I'll just like to say a couple of words about the institute. It's a small institute created in 2007, the fall of 2007, with a small membership, only 2,600. But it's quite different from the other institutes because most of the members are in academia or research. And as a result, it's a very productive institute, because what is expected from those members for their day job as professors or researchers is what we want them to do for the association, the Scientific Professional Association. And we do have 16, actually now 17 since October 1, 17 technical committees that address different parts of engineering mechanics. And the most recent committee is on architected materials. And we're going to have one established next week on machine learning in mechanics. Those committees are very active. They review papers for the Journal of Engineering Mechanics, which is very well-established and recognized journal, peer-reviewed journal. They organize sessions for the annual conference, which we usually hold at universities. This year we were at Caltech, last year at MIT, 2 years before at Stanford and Northwestern and so forth. And even though we have 2,600 members, we have 1,000 people coming to the conference, which is amazing. It means the conference is considered as a very valuable event where people can interact, exchange, network, and so on. We publish a few books, and also those committees do student competitions. I think last year we had 10 committee-sponsored student competitions. And when we say students, it's mostly PhD students, really. And it's really a very nice venue. And one of those committees is the Objective Resilience Committee, created in the fall of 2015, so it's only 4 years old, but very active committee. We have about 50 members in that committee, including Professor Bocchini and a couple of his students. That committee has had sessions at every conference since it was created, had organized student competitions, is working at every conference, is working on the manual of practice with about 30 chapters covering policy, technology, and applications, which should come out next year, probably about the summer, if everything goes as planned. The committee also organized 2 workshops, one at the University of Mississippi in March of last year, and one at Tongji University on the occasion of the EMI International Conference in Shanghai. And it also established, starting last year, an annual lecture on objective resilience. Last year's was the inaugural lecture given at the University of Michigan by Professor Paolo Gardoni of the University of Illinois at Urbana-Champaign. And this year we are pleased to have Lehigh University host Professor Jamie Padgett from Rice University, which is also the university of the president of the EMI, Professor Paul Spanos. So I just wanted to draw your attention to the fact that our next conference is at Columbia University, which is, stone's throw from here. It is also held in conjunction with the Probabilistic Mechanics Committee, another probability mechanics conference, another conference which is owned by EMI. And it should be a very, very nice event. I have brought with me some flyers for that conference, and the abstract submission opens today. I submitted my own abstract yesterday evening. Actually, it's open, so you're welcome to consider participating and submitting an abstract. We also have another conference in the UK in April. Have that as well, along with a brochure on EMI, so you can find out about EMI. But many of your professors, Professor Panos, Department Chair Diplas, Professor Bocchini, Dan Frank-Paul, they're all EMI leaders, and EMI is well known within Lehigh University. So thank you again for coming, and thank you.
So before we get to the main event, I have to do a very quick round of thanks. First of all, everyone in attendance, I want to thank you for participating. I see Dr. Snyder. The university is always very supportive of our initiatives, and I'm grateful. Second, I want to thank again EMI and the Objective Resilience Committee for promoting this and for sponsoring this initiative. Third, I want to thank the Civil and Environmental Engineering Department, as well as the Interdisciplinary Research Institutes who helped me in advertising this event as much as possible, as well as the local chapter of the American Society of Civil Engineers that sponsored this also for professional development credits for
PEs. Then I want to thank my research team that helped me a lot in putting this together. I'm very thankful. You are exceptionally talented students, and you're also team players, and the two things rarely go together. I'm proud of you guys. And last, I have to thank Dr. Jamie Padgett for coming here. I know how many things she's trying to juggle, and I'm very grateful that she came. Dr. Padgett received her PhD at Georgia Tech, and she's now a faculty member at Rice University. She receives a lot of accolades, including the Career Award, the Huber Award. She's involved in all the most important research initiatives in our field. I could go on forever. You see how packed her short bio sketch in the ad is. But I just want to mention two contributions that I found to be groundbreaking. The first one is that she was one of the first, maybe the first, that systematically really promoted the development of fragility curves for classes of structures, not for individual structures, but for classes that are one of those tools that are necessary for that shift from the study of an individual structure to the study of an entire system. And she was really spearheading this for Bridges. The second contribution is her continuous push for data collection and data sharing that is becoming, frankly, necessary for any area. It's particularly true for us in the area of resilience, and she really doesn't miss an opportunity to remind all of us to do this, even if it's not really in the culture of our discipline. It's changing, and she's one of the leaders that are changing this. So for all this reason, I'm very excited to hear what Dr. Jamie Padgett has to say. Thanks again.
Well, good afternoon. That was a very kind introduction. And I must say that I'm humbled to be invited to be a part of this lecture series. And I really appreciate the ASCE and EMI Objective Resilience Committee for inviting me to be a part of this series. And a big thanks to Professor Bocchini and to Lehigh for the outstanding hospitality so far. I really enjoyed the exchange. I'm pleased to have the chance to share with you some of the ongoing research in my group at Rice University, but also point to some of the collaborations and advances that I have seen in the field tied to resilience modeling, specifically with respect to transportation infrastructure and some of the linkages to looking more broadly at community resilience. For some of the students in the audience, I'll also try to point to not only perhaps well-established and published work, but some ongoing and open quests and open topics that I think still require a lot of attention in this field. I think it goes without saying that we can appreciate the potential impacts of a broad range of different natural hazards on our built environment, whether it be historic or recent earthquake events, hurricanes, or flooding events. And this really serves to prompt and promote better understanding of not only the physical performance of individual infrastructures or networks of infrastructure systems, but also better exploring and modeling some of those cascading impacts on our communities. And I pulled just a couple of different sources that I think did a nice job of helping to underscore some of the impacts of these hazard events on our built environment from different lenses. The first plot, which you may have seen, is some of the widely published data from NOAA, looking from about the time that I was born until present day in terms of those number of billion-dollar disaster events. So we note the increasing number of these events over those several decades, as well as some of the contributing hazards. And this is looking at a US nationwide perspective. I like some of the work from Pesaresi and colleagues that take a deeper look at trying to uncover some of the potential contributing factors to that with respect to looking globally at the exposure of either populations or area of development of our built environment. So we see that continual uptick in some of those contributing worldwide threats with respect to earthquakes or flooding or hurricane events, but also underscoring that with population growth and urbanization, we continue to be plagued with this challenge of mitigating the effects of natural hazards. We'll dive down a little bit more deeply to look at one specific piece of that built environment today, which is looking at transportation infrastructure. A lot of my examples today will be from bridge and roadway networks, or we spent a particular piece of effort trying to understand the individual components of these infrastructure systems. And we'll also look today a little bit more broadly at how they translate into that system level performance or interaction with the community. I pull an example here because it hits close to home for me. So these are images and maps from Hurricane Harvey that occurred in 2017. How many of you saw plenty of media reports about Hurricane Harvey out in the audience? Anyone live in or visit Houston during that time period in Texas? Some former Houston residents I know in the audience. This essentially was more or less in my backyard. So it always hits close to home when we're reminded of the potential effects that perhaps our work can have in trying to mitigate these events that affect our local communities as well. And we were reminded from this event when we're looking at perhaps roadway or bridge inundation or washout of structures of the short-term implications that can have on impairing emergency response operations, but also the long-term effects that can have in terms of repair and recovery of other systems or community functions. Also, we were reminded from some of the work that we did following Hurricane Harvey of the inequitable impacts that hazards may have on different residents of our communities. And so the map on the right was some of our study of looking at hindcasting of that Hurricane Harvey event, its impact on transportation infrastructure with respect to access to critical facilities like hospitals, but also looking at that intersection with different socially vulnerable populations or socio-demographic groups where we saw very high correlation between loss of transportation access to emergency services and indicators of social vulnerability. So with that, we'll take a look at diving a bit deeper into better understanding and modeling transportation infrastructure performance and resilience following these types of hazard events. We'll touch briefly on some of the key input models to that framework that has really been developed and evolving through a worldwide set of researchers. And I'll spend a bit more time looking at application examples, and we'll use those examples to point out recent advances and some continued challenges and opportunities before concluding today. So I'd be remiss if I didn't mention today, of course, the broad range of definitions that exist when we're trying to characterize the resilience of our structures or infrastructure systems, or perhaps look more broadly at the lens of community resilience. And I pulled just an example from the national academies that I think points out some of the very common concepts that we see in this range of definitions, and particularly like some of this work by Gasser and colleagues that serves to highlight the various concepts of resilience and just reinforce that idea that we're looking at various metrics. See how if I can do this, various metrics of system performance. And we're interested in not only that immediate post-event performance, but the time evolution as we seek to restore some metric of performance, whether it be load carrying capacity for a bridge or traffic throughput through a highway transportation network. And we see these notions of looking at pre-event planning, at absorbing these events, these punctuated hazards, and looking at that recovery timeline or adaptation over the infrastructure time horizon. So with that, I'll pose a very generic multi-hazard resilience framework. This is not specific to our own research, but just points to some of the key input tools that various researchers around the globe are working to try to help advance the science of resilience modeling, quantification, and hopefully, ideally, affecting resilience enhancement of these systems. So, of course, key to this notion is that we have to have a healthy understanding of the hazard potential, whether it be earthquakes, hurricanes, floods, and so forth. We need to look at that exposure, like the early examples I showed of that worldwide exposure to populations or developed areas. To be able to actually assess our infrastructure or structural performance, we need an adequate characterization of the spatial distribution of those structures, of their design details or other features, so that we can assess their behavior or response under these extreme event loads and their likelihood for entering some level of damage that we can correlate to metrics of performance, whether it be functionality or other cascading consequences like casualties or repair. Keeping in mind our notion of resilience, we're interested not only in that immediate aftermath of the event, but looking at the temporal evolution of various metrics. These could be functionality of the individual system, but we're also seeing increasing notions of looking at the intersection between our built environment and other social and economic systems when quantifying community resilience. A lot of what I'll be talking about today are some of the input models to this framework or examples of their integration, more from the analysis, modeling, and quantification perspective, but keeping in mind that our ultimate goal is ideally to support decision-making at various points in time in this resilience timeline. It may be with respect to pre-event planning in terms of prioritizing resources for upgrade or investment of these systems. It may be in the immediate aftermath of these events, looking at emergency response and where we deploy crews, or maybe more of a long-term planning horizon that we're trying to affect in terms of hazard mitigation. So just want to make a few notes about some of these key input models. First, with respect to hazard modeling, we're seeing increasing effort to look at fully physics-based simulations of some of these types of hazards. For example, earthquake hazards across a spatially distributed region. This has key advances in terms of looking at the response of our spatially distributed infrastructure, but also may pose challenges in terms of computational efficiency or demands, particularly when we're looking at full probabilistic analysis of the impacts of these hazards on our systems. We're also seeing increasing body of work looking at surrogate modeling of various hazards, whether it be estimating intensity measures of a site from an earthquake event or, for example, a hurricane-induced surge and wave event. And increasingly work that's looking not only at individual hazards, but multi-hazards from different perspectives, whether it be those cascading events like tsunami following earthquake, repeat events like repeated earthquake events or main shock aftershock simulations, or this idea of concurrent or correlated hazards, with that hurricane event being a prime example of the multi-hazard wind, surge, and wave event. And each of these pose challenges for us in terms of modeling and simulation, particularly in a probabilistic resilience quantification. With respect to exposure modeling, I'll just point to some of the challenges and opportunities that I see here. A lot of the work that I'll show you today is looking at transportation infrastructure, and we do have some luxury of publicly available databases for some of these systems. But as we look at alternative systems, we're increasingly posed with challenges of understanding even the characteristics of those systems at a regional scale. We see increasing efforts at looking at proxies for different performance indicators or characteristics of the structure, and increasing efforts to be innovative in terms of how we define our inventory, whether it be leveraging AI from aerial imagery or boots on the ground data collection and synthesis. In terms of characterizing the physical vulnerability of these infrastructure systems, here's where my group spends a large portion of their effort, is in terms of some of the fragility modeling of structural systems. The idea here is that we're characterizing the likelihood of damage to these structures or exceeding different limit states given some intensity measure of the hazard, or increasingly shifting towards not only the intensity measure of the hazard event, but also a set of characteristics that describe and define the structural system. So in this transition that Professor Bocchini mentioned from structure-specific fragility modeling to portfolio level or class fragility modeling, we have a lot of decisions and compromises perhaps to make in terms of introducing additional sources of uncertainty into our fragility modeling and also having adequate characterization of those systems. We've seen increasing trends in recent years, including some of our work, to introduce the notion of parameterized fragility functions that essentially help us to transition from these univariate fragility models where damage is conditioned solely on intensity measure for either a class of structures or an individual structure to perhaps a compromise, which would be a parameterized fragility model for a class. So we're looking at a class of structures, but now we can tailor our individual fragility estimates based on not only the intensity measure of that event, but some design details or characteristics of the structure that may be defined in either deterministic or probabilistic fashions. This could be things like the span length or the column height of our bridge or the reinforcement ratio. So some of the advantages to this type of strategy would be that on a regional scale, we can have advantages in terms of computational efficiency without deriving unique models for each individual structure, but perhaps have the advantage of considering structure-specific details from our inventory, where we can either propagate those uncertainties or introduce those design parameters from some of our exposure information data. I showed just one example form of that derived based on a logistic regression, which is the form that you'll see in a lot of the examples that I show moving forward, but this certainly is not the only option for those parameterized models. Very briefly, just wanted to highlight some of the range of different structural systems that are pertinent when we're looking at resilience of transportation infrastructure, some former and recent advances here. The first one that I show on the top left is looking at a structural system that's received relatively limited attention when we're looking at fragility modeling, especially at the class or the portfolio scale. So if we wanted to go and look at resilience of railway networks, formerly we had very little information on the fragility of these structural systems. And in many cases, we relied on their highway bridge counterparts as a proxy for looking at railway bridge fragility. But that really perhaps would have been an overestimation of the vulnerability of some of these systems if we don't consider the unique design details with rail track interaction, for example. And it really serves to underscore for those of you in the audience that we still lack a lot of input models to this resilience assessment framework as we look to apply it to different types of infrastructure systems. On the right-hand side, just an example of looking at another component of our transportation infrastructure with respect to roadway. We're looking in this case at roadway under hurricane hazard loading, considering in this case a fragility surface where inundation duration is a key predictor of that roadway washout coupled with distance from the shoreline. And this is a part of some of our ongoing collaborative work with researchers from the University of South Alabama, primarily informed by empirical damage data from Hurricane Ike. On the bottom left, I'm pointing to some work that we conducted about a decade ago now, but I think this notion has really gained momentum and interest in terms of looking at the joint intersection of different threats. Specifically in this example, looking at effects of aging and deterioration of bridge infrastructure when we're assessing its performance under hazard loading, suggesting that we cannot just simply look at that pristine structural condition when we're trying to predict its performance under hazards such as earthquakes. So this is some work that Jay Gosh did as a part of his PhD work that led to this notion of time-dependent fragility models for various structural systems. And then finally, at the right, just underscoring some of the parameterized fragility models for highway bridges that allow us to have that opportunity for what-if scenarios or looking at different design details. For an individual structure, exploring influences such as changing reinforcement ratio that can be useful perhaps in the design phase, or at the portfolio level, looking at influences such as span length or number of spans so that we can target and pinpoint some of the more vulnerable structures within our infrastructure network. Finally, I want to point to another key input model that I think is quite a challenging problem with respect to modeling the restoration, either at the individual structural system level or considering how those map to and integrate with the network level restoration of functionality. So fairly generic indication here that's been widespread adopted by various researchers, including groups like Professor Bocchini's here, to look at this idea of the time evolution of some metric of functionality Q over time, recognizing that we have some triggering hazard, some potential delay or time till initiation of recovery, and then looking at that time evolution of restoration of functionality. And not a trivial thing to try to model from an objective perspective. I'll note that within the transportation infrastructure realm, there's been quite a bit of work that has attempted to look at this, especially for bridge infrastructure, looking at some early stepwise restoration functions just for, say, in the immediate aftermath of the event, to work that's looked at that full time evolution of recovery or explored different model forms that could be introduced to characterize that recovery. A real challenge that I think we see with respect to developing these models is the need for data to either inform or train these types of models. So one approach that we've taken for doing that is to leverage survey data of owners, inspectors, contractors who would be performing either the post-event inspection or looking at modeling that restoration timeline, considering repair actions, and also collecting post-event, not only damage, but recovery information on that time to repair. So this is one potential approach where we have looked at decision tree models informed by that survey and empirical data to give us insights based on the combination of component damages to this system. What's the likelihood of, say, closure to the bridge immediately after the earthquake, or imposing load restrictions or lane restrictions or speed restrictions? This is particularly important if we want to make that next link between bridge infrastructure damage and transportation infrastructure performance, that we characterize that in terms of metrics that could ultimately tie to things like traffic flow or lane load and speed restrictions. An alternate or an additional consideration from that perspective is not only the immediate aftermath of the event, but looking at that repair timeline and evaluating things such as the time to either fully open that structure or remove some of these restrictions. So with that in mind, I want to move to a few application examples that I think will highlight some of the advances and challenges in this area. The first one that I want to look at is an evaluation of resilience to seismic hazards for transportation, bridge and roadway system, where we're looking not only of classical metrics of resilience, but also perhaps broadening that notion a bit to looking at other metrics of performance for these systems. We'll be leveraging a test bed in the greater Memphis area that I refer to as MMSA, the Memphis Metropolitan Statistical Area, or zooming in to a specific Shelby County example in the region. And this specific location is a part of an ongoing test bed as a part of the NIST Center of Excellence on Community Resilience Planning. Of course, one of our challenges is to first define that infrastructure system in terms of its exposure, the characteristics of the bridge and roadway system. I won't go into the details here on all of the data collection, but just an illustration of the type of network that we're dealing with here. We're looking at both scenario-based and probabilistic hazard analysis for this case study. I'll show you one example of a scenario earthquake event near the New Madrid seismic zone, where we're integrating some of those parameterized seismic bridge fragility models that I mentioned a few slides prior, and also some of those decision tree-based restoration functions for looking at that time evolution of component restoration of functionality. So here's one example where we may compare, for example, pre-event transportation network performance in terms of things like traffic flow through the transportation network, implying that we're coupling with this a flow-based analysis, which from our perspective, we are not transportation engineers. We're using what I will say is somewhat state of practice user equilibrium traffic flow simulation through this network to look at things like number of vehicles that are flowing through these links. In order to inform this, we need information on key origins and destinations in our system, essentially where drivers are tending to go in this system. Integrating those input models from the fragility and restoration functions, we can start to better understand that post-event condition, not only immediately after the event, which we're seeing here in terms of our color-coded closed bridges with our red X's, those partially open structures that may have lane or load restrictions, or the fully open structures, but also explore how that may evolve in time, both at the component level and how that translates into affecting transportation network performance with traffic flow through the system. In this example, by about 9 months after the system, although we still have some partially open structures, we have nearly resumed our initial traffic flow in the system. So one way of measuring time evolution of performance of that system. But I think this is really an ongoing discussion that we need to continue to have with respect to these types of resilience metrics, or ways that we may measure and communicate functionality of these systems. And it may be very different for different decision makers or stakeholders. From the perspective of transportation infrastructure, we often look at things like connectivity between different locations, say from a household to a fire station, or look at metrics such as travel time or travel distance that are often tied to things such as indirect consequences on the community. We, of course, can broaden that notion to not look in isolation at the transportation system, but the intersection, for example, with social or economic systems, looking at other metrics of performance over time. And I think this starts to have a lot of interplay with discussions that we're having surrounding sustainability of our systems, and perhaps looking at hazard performance through that lens of sustainability, where we measure things like the waste that's generated from damaging, repairing, rerouting within the system, or the emissions associated with that, embodied energy associated with those repair or rerouting actions. May again be other, perhaps broader resilience metrics that we consider through the sustainability lens. There are also a lot of different suggestions in the literature with which we might quantify these individual metrics of this time evolution, considering integration above or below the restoration timeline, and work like that from Frangopol's group here at Lehigh that suggested we need to be transitioning to looking towards life cycle measures of resilience with the potential for multiple or repeat hazard events. So all of these, I think, worthy discussions as we continue this pursuit. One thing that I want to put out there, of course, is perhaps the need to better offer guidelines on the resolution of some of these types of models when we're answering different questions or measuring different levels of performance. For example, with that same MMSA network, we looked at various measures of performance such as travel time, travel distance, emissions, or missed trips. And as we look at different resolutions of our transportation network, of course, it can have a very significant impact on the measurement of these resilience metrics. I also think that points towards the fact that we should perhaps be more interested in relative comparisons of some of these measures at this stage rather than some of those absolute estimations of either deterministic or probabilistic metrics of resilience. And lastly, I want to point to some of the opportunities that I think this can pose in terms of looking at perhaps at a system level, identifying what are our kind of dominant contributors to these measures. So if we're looking at emissions over the transportation network, which key vulnerable bridges, the damage of which structures are contributing most to the emissions that we see. This could be a way to help target pre-event investment in retrofit or upgrade, depending upon what your metric of interest may be. It doesn't have to be emissions. The other way we can look at this may be at the structural system level. And this is just an example of some work that we've been doing in collaboration with my colleague at Rice, Leonardo Duenas-Osorio, at looking at risk-based component importance measures, where we essentially identify which bridge components, whether it be the columns, the bearings, or the abutments, are responsible or tied to us exceeding various risk thresholds. This may be target risk thresholds with respect to cost, emissions, travel time, however you want to define that risk performance measure. But it helps us perhaps to have a transition from our traditional reliability-based component importance measures to looking more broadly at social, environmental, or economic implications of these structural systems. With that, I want to transition to an application example that moves us beyond individual modes of transportation, like our bridge and highway network, that I think has received a little more attention in the resilience modeling community, to looking at railway systems and this idea of intermodal resilience of networks, where we consider the potential for transport of goods or freight across these different systems. We're again using that same MMSA testbed around the Memphis metropolitan area. So some of the ongoing work of one of my students, Sushreyo Misra, is looking at defining a probabilistic resilience framework for rail and truck intermodal systems under seismic hazards, essentially considering the potential for freight flow across these two systems. There's been quite a bit of work from more of the operations and logistics perspective of looking at resilience of these intermodal systems, but we find that we're lacking a lot of the key input models in order to adequately assess the performance of either the individual or the combined systems. I showed you the example of the railway bridge fragilities or some of those restoration functions that we're deriving not only for bridges, but also rails and roadways that inform this type of modeling. Some of our ongoing work is looking at what I think is an interesting challenge in these intermodal networks, which is not only the railway network or the highway network alone, but where they come together for goods transfer. This is essentially a complex system in and of itself with respect to the terminals. We have cranes, we have the potential for warehouses, we have other systems such as fuel that are important for that freight flow transport. And so each of those have their own constituent structural systems and functionality that are required for informing the intermodal network functionality. I'll show just a few examples of that MMSA system in terms of the range of different metrics that we may be interested in. It could be things like cost to the shipper. This is perhaps one of the dominant metrics important for determining if the shipment will be taken. We could look at indirect effects such as cost to the environment or the potential for accidents, or freight flow value that's disrupted. And this is perhaps one of the most direct links with some of our colleagues that are looking at economic impacts at a regional or nationwide scale. An illustration on the right is showing an adaptation of a functionality metric that was proposed by Miller Hooks, where we're essentially adapting that to look at the time evolution of post-event to pre-event throughput in that intermodal network, which is shown in the figure at the top. So what are some of the implications of these types of models? One thing that it's pushed forward for us is the importance of perhaps looking not only at multi-resolution but multi-scale analysis, especially when we're talking about things such as freight flow, where we don't have these perfect boundary conditions around, say, Shelby County or the MMSA case study network, but there is the potential for local damage to affect that nationwide freight flow. And that's led us to look at perhaps high resolution models with all of those individual components like the intermodal stations in our local region, but looking at perhaps coarser models across the nation for flow of goods that could be rerouted around our affected regions. It's also allowed us to have better opportunity for coupling with some of our colleagues that are looking at these regional or nationwide CGE models of economic impacts. With that, I want to take a bit of a shift down the coast. So we've been looking up in earthquake country in the central and southeastern US, and I want to use a couple of final examples that are closer to home for me. We're shifting towards the Texas coast. So now in this multi-hazard context, we're considering the potential for hurricane events and their impacts on our transportation infrastructure. But in this example, I want to shift to looking at not only the impacts of, say, bridge and roadway damage on the transportation network performance, but how we might link that with other systems such as petrochemical facilities or refineries that have their own models to characterize their performance. So we'll be looking at this idea of performance of components within a refinery along a coastal region. In particular, the potential for damage and spill risk to above ground storage tanks in these refineries. And one of the key questions that we're trying to answer in this problem is, can we actually access these high spill potential locations quickly during or after a storm? And also, what are the broader implications perhaps for things like human resourcing or staffing? Can workers get back to resume business operations or for intervention activities? So generally, you see our integrated framework and some of the key inputs. We spent quite a bit of effort developing some of these tank vulnerability models in recent years. And we'll be integrating some of the bridge fragility models for looking at unseating potential from hurricane coupled surge and wave action. In these examples, we're using scenario storm simulations that I'll be showing you, with the potential to extend that to more of a fully probabilistic hazard analysis. And some of our key questions, again, would be looking at whether we can reach these high spill risk locations, because not only of the potential for bridge damage, like the unseating case, but that time evolution of inundation of bridge and roadway that affects short-term functionality as well. In terms of some of those input models, we spent a lot of effort developing some of the exposure or inventory data, processing aerial imagery, as well as relying on permit information, publicly available databases, reverse engineering the design of some of these structures. So it doesn't perhaps always get a lot of appreciation, but there's a lot of effort that goes into building these types of case studies. The two different scenario storm events that we're considering are based on some work that was done by the U.S. Army Corps of Engineers with coupled ADCIRC and SWAN models, essentially high fidelity simulations of surge and wave potential. We're integrating those parameterized fragility models that predict the potential for tank damage. It could be failure from uplift or from shifting or overturning of these tanks that may lead to spillage of hazardous materials like crude oil. Also, from the perspective of the bridge vulnerability modeling, we are considering parameterized fragilities where unseating is predicted based on characteristics such as maximum wave height or relative surge elevation. The illustrations on the right just serve to underscore the time series that we're considering, and I'm specifically focused on a relatively short time horizon in this example, where we're considering that full time evolution of the storm passage, looking at not only, in this case, essentially the surge time history, but also on the top, looking at that time evolution of failure probability of those tanks, which may lead to spill risk during the storm event. That's where we particularly want to look at focusing on, can we access these high spill risk locations, considering that we may have the potential for removing nodes or links in our transportation network because either the bridge is unseated, the road is washed out, or we have inundation of those assets. We'll be looking at different metrics such as connectivity loss, travel time, or travel distance for an example. So this is just one example of those deterministic scenario storm events where we're assessing things such as failure probability of the tanks. These little dots, higher or warmer colors indicate higher failure probability. And all of the squares on the map show you those bridge failure probabilities. And then you're seeing the roadway network as well as key locations of facilities like fire stations, from either the approximately 100-year surge at a specific location in the ship channel or approximately 500-year storm surge event. We use that to look at different things such as that increased travel time from emergency services to the high spill risk locations, or looking at time evolution of things such as census block access back to the refineries. And this can have key implications from an owner or operator perspective. A lot of times there may be definitions, for example, that those that work in resuming business continuity or an emergency response perhaps need to live within a certain radius of the facility. Well, that may not be the best way from a risk-based perspective, looking at likelihood of being able to actually reach the facility from your home. So we may be very close to the facility, but have very low potential of actually getting back to help with cleanup or resuming business operations. So one other perspective of how that transportation infrastructure resilience can perhaps inform various stakeholder decisions. So I want to leave you with this last application example, which is integrating some of these transportation resilience models into a broader assessment of community resilience under hurricane hazards. This is a part of a large collaborative effort, in particular with colleagues from Texas A&M, from social sciences, and from Oregon State University and the U.S. Naval Academy. In this example, we're looking not only at bridge and transportation infrastructure, but the potential for building damage from these multi-hazard surge wind wave events, and coupling that with social systems models that characterize household level sociodemographic information for the community and use that to inform models such as the likelihood of evacuating prior to a storm event. We're using this to compute what we refer to as hybrid metrics of resilience, essentially implying that we require this coupling between social and physical systems to even evaluate some of these metrics to inform decision making. In terms of the hazard modeling for this particular case study, we're transitioning from those scenario storm events that I showed you in the past application example to the potential for fully probabilistic hazard simulation. The way that we're achieving that is by leveraging surrogate models of the storm intensity measures using Kriging surrogate models. This follows generally the approach that was proposed by Teflonidis and colleagues, but extends that to look at other metrics such as inundation duration that we find is a key predictor of things such as roadway washout, as well as joint surge and wave intensity measures at the site. Key predictors of this model would be things such as the angle of approach, the landfall location, or the radius to maximum winds. The advantage of this is we can very efficiently approximate these IMs and afford things like hundreds or thousands of realizations of the storm at the site of our building, bridge, roadway infrastructure. These are some of those hurricane fragility models that I mentioned earlier. where we're predicting unseating potential given relative surge and maximum wave height. And then again, looking at the potential time evolution of restoration of functionality of these structures. Roadway washout based on some of those recent empirical roadway fragilities. In this example, we're moving beyond some of our simplifications from the earlier studies that I showed and considering that we perhaps don't have perfect availability to crews and resources to conduct repairs of these structures. So now we're looking at things like constraints on crews and how we look at deploying these. We may have perhaps very optimistic assumptions with respect to prioritizing crews based on their importance in the transportation infrastructure. Or we may look at a system where we're perhaps lacking some of those knowledge from an objective perspective. So this is just one example of looking at operability in terms of being able to, those fractions of different origins and destinations that we can reach, but considering the fact that we have constraints on crew availability, but perhaps a more optimistic assumption that at least those resources are deployed based on the priority in the transportation network. With that, we can look at measures such as connectivity between various households to inland off of Galveston Island, or look at things like access to fire stations or medical centers. We have the potential for looking at this now at the household level as well, and integrate things like the potential damage to the residential structure, as well as the access to that structure, and are we likely to have someone that's still inside, a non-evacuee. This is what we're referring to as hot households, which is essentially kind of a worst case. You're in a vulnerable structure that's likely to be damaged, you haven't evacuated, and you can't be reached by fire or emergency services. So this could be a great way to look at targeting either communication strategies, support for evacuation, or where we may look at investing in pre-event risk mitigation activities. Again, looking at that from both the scenario basis or thanks to the efficiency of those surrogate models, looking at annual probabilities of exceeding these different measures. So finally, I want to note what I would consider a few challenges and opportunities that still remain in addition to the ones that we discussed throughout the talk today. One is with respect to hazard simulation, in particular, respecting some of the correlation structures between these various IMs across our spatially distributed infrastructure. And I pose this is a particularly increasing challenge when we start to look at more advanced intensity measures that perhaps we find are excellent predictors of structural performance, but we don't have adequate models to characterize that covariance matrix for, say, realizing random fields of these hazards. Also becomes perhaps increasingly challenging when we look at tailoring individual intensity measures to each structure across our spatially distributed system. We've been doing a bit of work looking at that, leveraging a spectral averaging intensity measure that's been shown repeatedly to be a fairly good predictor of structural response, but perhaps we lacked an adequate co-simulation method for these IMs. But plenty of work, I think, left to do in that area, and I know some great work ongoing here at Lehigh there. Also, I think when we're looking at these various complex systems exposed to multiple hazards, we are increasingly facing the challenge that, one, we have many structures that we still have yet to adequately characterize their performance in multi-hazard loading conditions, and two, that we may have multiple response quantities of interest that we'd like to predict. For example, we may have the case of the bridge that we looked at where we're interested in column response, bearing response, abutment response, all important for characterizing failure modes of these structures. We see a lot of effort tending towards exploring different types of surrogate models so that we can do this efficiently without always having to perhaps rely on high fidelity simulations, for example, with fluid structure interaction for these coastal structures. But I do think there are still quests in this area, particularly when we look at this idea of complex structures with multiple important predictors of response, where some of the traditional approaches have been to develop individual surrogates for the response of each of those of each of those components, like the columns, the bearings, the abutments, where our alternative may be to train an individual model, what we're referring to as this multivariate surrogate demand model, so that we can adequately characterize the response of multiple important predictors of damage, as well as preserve some of their correlation structures through what we're referring to as this trend and error covariance model. And then lastly, I think we have a great opportunity to transition towards what I would refer to as a notion of smart resilience. So this is looking at how we can increasingly leverage diverse data sources for informing some of our models or our decision actions throughout this resilience timeline. I showed just an example of some of the different data sources that we're looking at leveraging for the flood and transportation infrastructure problem, whether it be things like camera data or authoritative data from inspectors, among other types of crowdsourcing data. Looking at, for example, improved situational awareness in the immediate aftermath of the event, where we look to fuse data, for example, from radar rainfall with physics-based simulations that some of our colleagues are conducting, with looking at transportation infrastructure performance and network accessibility studies. This particular example offers a model that we've been developing for real-time flood alert and access to critical facilities during floods that essentially could deliver this information to the public or key stakeholders. But I think lots of opportunities to infuse different types of data sources. For example, looking at dynamic Bayesian networks for incorporating and updating this time evolving process during the flood event. So with that, I'll leave with a couple of key messages. I think we have what's generally been accepted as an approach for modeling resilience to these systems, but a lot of the key meat and interesting challenges are in the details there for how we achieve that integration and how we achieve accurate and efficient models for those types of simulations. Some opportunities, for example, with respect to surrogate modeling, looking at uncertainty quantification and propagation, and looking at how we can actually inform practical decision making for improving resilience of these systems, and a few challenges of many that I note from those challenge topics. So I want to acknowledge some of the funding sources for the work that I've drawn on, especially for the different application examples, in particular from NSF and from the NIST Center of Excellence. And a big thanks to the research group, the team of students and postdocs at Rice, whose work I'm really just representing here. See an image of some of them last year, but the examples that I'm showing are spanning a couple of generations of students. So thanks for your time, and I'm happy to answer questions.
So we have some time for questions from the audience, if anyone. David.
Early on, you showed a slide of decision trees, and I think that was have you or do you know of anybody who's looked at how whether or not the types of probability that you're developing?
Yeah, that's a great question, and I think what I have seen is there have been a couple of different schools of thought for trying to model restoration and recovery. What the approach that we're taking here, as you imply, is not necessarily reflecting what the ideal or optimal decision is, but it is perhaps the likely decision, or at least the recommended decision by some of these experts. We're also muddying those waters in some case because we're combining that with empirical data on what actually is happening during the events. So I will reinforce, I guess, the motivation to your question, which is indeed we're trying to model the likely subjective decision making, but I cannot say that we have truly compared that to what would be the optimal decision under that perspective. My hunch based on observation of a lot of that data is that it may not per se be the optimal decision, at least if you compare that objectively to what perhaps a construction management timeline would suggest that you could achieve. But I think it's a really challenging problem to try to optimize, and I'm speaking at the structural system level. I think it's a whole nother ballgame when you move to the transportation network scale and look at how actions actually play out. We have not attempted yet to model how what I would call that subjective process at the transportation network scale. What we're simply doing is imposing potential constraints on that and alternative ways you can assume that plays out. And that, I think, is where we're still lacking a lot of the data for model validation that we talked about early on, is particularly at that system scale. Do we have the data in order to model or validate that time restoration of things like travel time through the system, or more extended metrics like the emissions in the system that I posed today? The very fair quest continues there. Yeah. Right. Yeah, so I will be very direct and say that that was not our work, and frankly, that was work that was done before we initiated this collaboration. But I'll give some props to Shannon Van Zandt's group at Texas A&M and some of her colleagues who conducted household level surveys from Hurricane Ike for a series of different years. I believe they even did repeat surveys after Hurricane Harvey, and asked questions about, did you evacuate or not? What affected your decision to evacuate prior to the event? And they developed some, from a statistical modeling standpoint, a fairly simple statistical regression based on sociodemographic factors and some of the influencing behaviors from their survey data.
Sort of a follow-up to David's question. You've made it clear that the accuracy of your input models is extreme. Are there cases in which models that might be used from the resources?
Yeah, I do think this is still a question that requires more attention, but I'll give you some of my initial insights based on the studies that we have done. I think it very much depends on that time point where you're concerned about measuring performance. If it's in the immediate aftermath of the structure and we're looking at damage prediction, from some of the work that we have done and others in the literature, some of the uncertainty and hazard characterization across the region may be dominating our uncertainty in performance. But when we're going to these longer time horizon regional simulations of resilience, then I think one of our largest sources of uncertainty is stemming from some of those functionality recovery models for the components of those transportation infrastructure systems. But that is, I will say at this case, still anecdotal based on case study exploration. I think we need a more systematic evaluation of that. Yeah. So that's a great question that in fact Professor Yang and I were speaking about earlier, and I will directly say that we are not in any of these examples considering post-hazard shifts in demand on the transportation infrastructure, and I admit that is potentially a gross assumption. For things like connectivity, that's not as central, but if you're looking at metrics such as travel time and considering congestion, then that's a really important factor. And I think it requires us doing much more coupling with other systems as well as social systems modeling. So the key would be, for example, maybe your business is closed, maybe your child's school is collapsed and so no one's going to school and you don't have those same origin destinations that you would have pre-event. All of the comparisons that I have assume equal pre and post-event OD matrix. And I think that is a very fair comment that requires further work. I've seen some recent interesting studies, especially looking at things such as power and water, that are looking at if we look at things like not only evacuation, but longer term population dislocation, then we can leverage that data for informing our demand on infrastructure systems. And we've yet to do that in the transportation applications here. Yeah, I think that is a very fair question, and I'm sort of going to punt on that in the sense that I personally don't anticipate that in our work we're going to be developing new time evolving or non-stationary hazard models of the occurrence or intensity and frequency of these events. But I do see the opportunity not only from the hazard modeling perspective, but just the overarching risk assessment framework, how we deal with realizations of these non-stationary events and how we start to couple that with other perhaps chronic stressors. So it's perhaps the changing climate, but also we have that time evolution of structural system, which is kind of more in the camp that we're coming from, which is being able to characterize not only the event occurrence is evolving, but the characteristics of the structure are changing in time as well. So I think some real key opportunities there that we've tackled more from the structural system evolution perspective, but not the hazard event occurrence perspective.
I have a question about surrogate models. You presented fragilities as a surrogate model for the structural performance. You mentioned the cringing models for hazards as a surrogate for hazards. How about recovery? Do you have any idea for good surrogate models for recovery?
Yeah, we have been toying with that at this stage, but I wouldn't say that we have any solid results to present. And the biggest challenge that I'm seeing there, and it kind of goes back to a discussion we had earlier, is adequate availability of data to train some of these models. I think it's leaving us with some more simplified notions of basic regression models or some of the decision trees that I showed without being able to exploit all of the advances of some of the modern, say, machine learning techniques. So perhaps as we shift towards that smart resilience notion that I mentioned, where we are leveraging streaming data sources, and we could use something like camera data to actually monitor that repair and recovery timeline of a structure, then we may be able to build up large data sets for that type of training.
Any other questions? Okay, then thank you again.
Okay. Thank you so much.
Thanks, everybody.